Okay, Algebra, this section kind of goes with, or this part goes with section 8.7, excuse me, 8.7, contingency tables. These contingency tables, which I think is kind of a fun word, also are sometimes called two-way frequency tables. And I really like analyzing or looking at two-way frequency tables because there's a lot of research and developers out there that actually analyze stuff on a two-way frequency table. In fact, there's probably a lot of people right now that are doing analyzing accuracy with the coronavirus using these frequency tables. Okay, so here's what kind of one of these. There's three problems here. We're going to go through each one of these. And I'll embed some questions in here as we go along. So um, we'll just do these three problems and then we'll be done. But they're going to give us some data on some accuracy and some tests that are run, and we're going to fill in a table. Okay, there is a 2.5% probability that a Schnauzer breed of dog coming for a visit to a vet clinic has a certain type of skin cancer. Okay, so 2.5% have cancer. Okay, have a certain type of skin, well, it says skin condition. Have condition. I'll put have skin condition, not skin cancer. Skin condition. The vet has a test that is 94% accurate. Okay, so test accuracy. Okay, so 94% test accuracy. Okay, those are the two things that it gives me. And it says the vet decides to treat every Schnauzer that tests positive for the skin condition with a prescription topical ointment. Okay, now if a test is only 94% accurate, no, there is not one test out there in existence for anything that is completely 100% accurate. Like pregnancy tests are not 100% accurate. Tests for cancer are not 100% accurate. We're going to talk about that down below here. J.C. Himmelberg, I don't know if you guys remember him when he was he graduated last year, when he was a seventh grader, was diagnosed with cancer because he had some blood work run and tested positive for cancer. But it ended up actually being a false positive because the test wasn't 100% accurate. So he was one of the people who was in that lucky 1% that it flagged and said you have cancer when he actually didn't. So we're going to talk about that down below here. But not every test is 100% accurate. So what they're doing is, even though this is only 94% accurate, which means 6% of the dogs actually don't have this skin condition, they're treating every one of them anyway. So all of these dogs that are testing positive for the skin condition, they're treating them, but 6% of them actually don't have the skin condition. They're just getting the ointment anyway, okay? So complete the two-way frequency table to represent this situation, assuming a total population of 1,000 or 100,000. We're going to start with our total number is 100,000, okay? And that's usually what we do with all our frequency tables. It just makes it easier to kind of compute values when we have like a really large number to start with. So every single time we run a frequency table, we're going to go ahead and start with 100,000. It just makes it really nice numbers to deal with then, okay? Now, 2.5% have the condition, okay? So that has this condition. That's total that have the condition, okay? So we need to figure out what 2.5% of 100,000 is. I take 100,000, and 2.5% as a decimal is 0.025. Okay, so I'm going to multiply that. So that means that there's only 2,500 or 2,500 that actually have the skin condition, okay? Now, if 2,500 out of 100,000 have the skin condition, then how many people don't have the skin condition? Well, I can just take 100,000 and subtract the 2,500, okay? And that means that there's 97,500 that don't have the skin condition, okay? Because the skin condition is not very, not a lot of dogs have it. Anyway, in the first place, so that's kind of why that split is there. Now, the test is 94% accurate, and what that means is 94% of the time, it's going to tell me the truth, basically, okay? So if my dog has the skin condition, they should test positive for it, right? Okay, so I'm going to put a little star in this box. they have the skin condition, they should test positive for it. They should not test negative when they have the skin condition. So reading this box and looking at this column, this should not happen. This is a no. That shouldn't happen, okay? In addition to that, if they don't have the skin condition, they shouldn't test positive for it. So this should not happen. That should be a no. And if they test, or if they don't have the skin condition but test negative for it, where these two columns come together, or this column and this row, no skin condition, those people should test negative. So this is what should happen, okay? Now, the things that should happen, or the truthful things that should happen 94% of the time, right? And then 6% of the time, it's going to do what it's not supposed to be doing, right? The test is not doing what it's supposed to be doing, okay? So looking at this total, 2,500, 94% of those 2,500 are going to get the results that should happen, okay? So 94% is 0.94. 0.94, let's go back. 0.94, and I'm going to multiply by 2,500, okay? And that's going to give me 2,350, okay? So out of this 2,500, 2,350 are going to get the results that should happen, okay? 6% of the time, they're going to get results that shouldn't happen. So what I can do is I can take that 2,500 times 0.06, which is 150, or I could have just taken this 2,500 and subtracted the 2,350 to get 150, okay? Because these two added together should give me my total over here, okay? So hopefully this table is kind of making a little bit of sense, right? Now, of these 97,500 that don't have the skin condition, 94% of them are going to test negative, like they should. So 0.94 times 97,500, and that is 91,650. Okay. So this time I'm just gonna subtract. I could take this 97,500 times that 6%, but I'm gonna subtract them this time. So 97,500 minus the 91,650 instead. This guy should be 5,850. Okay. So you would have gotten that answer if you took 6% of that, or if you subtract it. It doesn't matter. Okay. So test negative, the total number of negative testers that I had out of the 100,000 was 91, let's see, 800 if I add those two together. 150 plus 650 is 800. Okay, and if I add these two together, oh my goodness, 0, 0, carry the 1, that would be 2, carry the 1 again, 8, 8,200, okay? Or I guess I could have just subtracted these two, right? And that would give me 8,200, okay? So find the probability of the skin condition given that the test result is positive, okay? So let me do this. Given that the test result is positive, we're going to start with that. The bottom number is going to be the test result being positive, okay? So how many total positive testers did we have? 8,200. And find the probability of skin condition. So of those 8,200, how many actually had the skin condition? 2,350 had the skin condition, okay? So if I figure that out as a probability, 2,350 divided by 8,200 is 0.29 or 29%, okay? So find the probability of the skin condition given that the test result is positive. Okay, so this is the really alarming thing. If you test positive, there's only a 29% chance you actually have the skin condition. That's crazy, okay? So this is where the results really, really, really break down. Yeah, it's just crazy. If you have a positive result, there's really only a 29% chance that you have the skin condition, which means that we're treating dogs with the skin condition that don't actually have it. Do you think it was a good decision of the vet to treat every dog that tests positive? No. Only 29% actually, let's see, T-U-A-L-L-Y, need treatment. Okay, so what would be a better idea is to run that test again, and the chances of getting 2 false positives in a row are really, really, really slim. Way, way, way more slim than 94%, okay? So they would run that test again, which is exactly what they did with J.C. Hummelberg. They ran the test the first time, they said, oh my gosh, you have cancer, and then they ran it a second time, and then it finally said, no, you don't. And then they didn't actually treat him for cancer. They found out that it was a staph infection and, treated him that way. So that would be a better option to do, okay? All right, I'm going to go through this one a little bit faster. So a veterinarian knows that 1% of dogs in the country are infected. 1% infected. Okay, and our test for the virus is 98% accurate. Okay, this means that it returns a positive result 98% of the time if the dog has the virus. It returns a negative result if it doesn't have the virus. So basically, it's telling the truth. It's being truthful 98% of the time. Okay, so we're starting with 100,000 dogs. 1% of those dogs is infected. Okay, 1% of 100,000, if you want to take 0.01 times 100,000, that would be that as a decimal, but you're just going to move that, 3 places? 1% are infected, so the total number that has the virus is 1,000. So it's going to be 1,000 dogs. That's 1% of 100,000. It's 1,000. So how many are not going to have the virus? If 1,000 have it, out of 100,000, that means 99,000 are not going to have the virus, because the virus is not very prevalent. It's not a really widespread virus. Okay. All right. Now, 98% of the time, the test is going to do what it's supposed to do. So if I have the virus, I'm supposed to test positive. Okay. I'm not supposed to test negative if I have the virus. If I don't have the virus, I'm supposed to test negative. So here and here, it's doing what it's supposed to do, right? And this is happening 98% of the time, okay? 2% of the time, it's doing what it's not supposed to. The test result is giving me false answers, basically, okay? So what I need to do is I need to figure out what these values are here, and kind of, make some conclusions based upon that. So 98% of 1,000 is 980. Okay, 2% of 1,000 is just going to be 20, right? Those two added together have to be 1,000, okay? I'm doing this math in my head because I know what 98% of 1,000 already is. Like 98% of 100 would be 98. 98% of 1,000 is 980. You're just adding another 0 on the end there, okay? This one, I can't do that in my head. 98% of 99,000, 0.98 times 99,000. This is 97,020, okay? All right, so if I subtract that from 99,000, okay, I get 1,980, okay? Or I could have taken 2% times 99,000 to get that number also, okay? So adding these columns together, the total number of people that tested negative was 97,040. And the total number of people that tested positive was 0,692. Yeah, 2,960. Okay, all right. The vet decides to treat any dog that tests positive for the virus. Okay, so let's look for testing positive. The total number of people, so total positive. This is really the results that I really want to look at. I want to look at total positive on the bottom, but I want to look at actually have virus on the top, okay? So out of the total that test positive, the total that test positive is 2,960. The people that actually have the virus, so the dogs that actually have the virus, there is 980 out of them, okay? So of the total number of people that are testing positive, 980 divided by 2,960, that is 0.33, which means that 33% of the dogs who actually test positive are the ones that actually have the virus. So 66 or 67% of the time, the dogs that test positive don't actually have the virus. Okay, so it's really a lot more frequent than people think. Okay, do you think this is a good decision to treat any dog that has a positive virus? No, only 33% actually have virus out of the ones who test positive. Only 33% actually have the virus. Okay. All right. Last one. It is known that 0.05 of the watches at a manufacturer are defective. 0.05% are defective. That's a pretty good stat. okay, 0.05. Now keep in mind that 0.005% is actually 0.0005 as a decimal. Okay, so that's the decimal that we're going to use, okay? And we have a method of testing the watches that's 98% accurate. So 98% of the time it's going to do what it's supposed to. Okay, 98% accurate, okay? So I set this table up and I went ahead, so you might want to fill this in. We have our test at the top here, so it's either going to test defective or it's going to test that it's fine. Like a defective watch would be something that, you know, like maybe the hands on the watch don't move the way that they're supposed to or whatever. So testing defective versus not testing defective. And actually being defective and actually not being defective are the results that I have on the side, okay? So we're going to start with 100,000 watches down here, and 0.05% of them are defective, okay? So the total number that's defective is 0.05%, okay? So if we take 100,000 and I want to multiply that by 0.0005, that's going to give me the total number of watches that are defective, okay? So that's only 50 watches. 50 watches that are defective. Now, how many are not defective then? That would be 99,050. Okay, because those two added together are going to be 100,000. So I just did that mental math in my head. 98% of the time, the watches are going to do what it's supposed to do. Okay, or it's going to give me the result that it's supposed to give me. So if it's defective, it should test defective. If it's not defective, it should test that it's not defective. Okay, so 98% of the time, it's going to do these two things. Okay, 2% of the time, it's going to do what it's not supposed to. It's not supposed to test defective when it's not defective. Okay, but sometimes that happens, right? So out of these 50, 98% of them are going to test defective. So let's figure out what 98% of 50 is. 0.98 times, go down here, 0.98 times 50 is going to give me 49. So 49 of them are going to test defective. Only one of them is going to test with no defect. So it's actually going to be a broken watch when it's like saying that it's perfectly fine. Okay, and then you're going to have customers. You're going to have one customer out of the 100,000 that's really mad. Okay. This one down here, 98% of this 9900, 0.98 times 99050 is 97,069. Okay. I don't want to have to subtract that. We're going to do, let's go back through and let's just change this to 0, 2. So I'm going to change this and I'm going to find the 2%. Rather than subtracting them, I'm going to do 2% of 99,050, and that gives me 1,981. Okay, now let's talk about this category. This person up here, this is the one customer that's going to be mad because they have a defective watch when the watch is saying, oh, it's not broken, you know, there's nothing wrong with it. But these ones are not defective, which means they're perfectly fine watches, but they're testing and saying that they are defective. So I'm guessing that these almost 2,000 watches here are just going to get tossed for no reason, right? These are just going to get thrown out, probably in a dumpster somewhere when they're actually not defective, but they're testing and saying that there's something wrong with them. Okay, so that's kind of depressing. 97,070, if I add these two columns together, I don't know, I can't do that in my head. 49 plus 1981 is 2030. Okay. All right. So now the engineer tests some of the watches and discards any of the tests that show to be defective. So that's kind of what I was just talking about. Of the total defective, I'm going to put total test defective. Okay. So we want to look at the total test defective, and we want to look at the actual defective. Okay. So there are actually 49 out of 2,000 that are defective, right? Okay, so if I figure that out as a percentage, 49 divided by 2030 is going to give me 0.02, let's say, so 2%. So what this means is that only 2% of watches that test to be defective actually are defective. So what's happening is 98% of the watches that we throw out being defective are actually good watches. So we're completely wasting money. So we probably should run that test again to make sure that they are in fact defective before we throw them out. Because yeah, otherwise we're wasting money in our company. Okay, so that was a lot of data, a lot of work. 3 examples. They were really similar to each other. But hopefully that can kind of show you that, results aren't always the way that they say they are, and that type of thing. So I like doing these tables. I think it's kind of cool the way that they all fit together. Okay.